So the next topic will be actually the boundary conditions. And boundary conditions are very important in computational analysis because it's actually represent the constraints that you apply to your domain boundaries so you got the right solution. So if you want to go for the definition here, boundary condition is presenting the constraints applied to domain boundaries. So you set up your domain, then you have to tell me what's the condition here. This is your boundary. You have to tell me the condition. Boundary condition could lead to one of two things. Could lead to no solution, or actually could lead to a huge error in your numerical solution if you don't carefully sign up your boundary condition. Let's give an example here. Let's assume that I'm dealing with two-dimension plate. Then I set up the boundary condition here. A temperature is 0 degrees C, and this boundary here is 50 degrees C, and this boundary here is 75 degrees C, and the boundary here is 60 degrees C. Then I ask you to find the two-dimension temperature distribution inside that place. So you're gonna set up your grid or mesh, right, to determine what is your nodes to get the approximation solution using the numerical analysis here. So you're gonna get the temperature at these points here. What the boundary condition is telling me here, the temperature within that plate has to be within the boundary temperature. So you have to get your temperature somewhere within that range. If you got one of these temperature above 75, 80, 90 degrees, something is wrong. I'm excluding if that plate has like internal source of energy or a heat generation. I'm just looking to a simple conduction problem here. Your nodes, the mesh data or the grid data has to be within the boundary condition. That's why it's called the constraints. It's your bounding value of your solution. That's number one. Let's take another example here showing that you may not get any solution. Let's assume that you have a pipe and you would like to get, you have the inlet velocity, Vn. Let's assume it's 1 meter per second. And you would like to get the velocity distribution inside this guy here. So you set up your grid or your mesh, right? And you will get the velocity somewhere here. And at the exit, this is your inlet boundary. At the exit boundary, maybe this is a fixed wall. It's a pipe, right? So the velocity here is 0. Same here, velocity is 0. That's a fixed wall. Then for the same mass flow rate, for the same pipe diameter, you ask me to set up the velocity at the exit to be 2 meters per second. Now let's look to the boundary condition. Velocity 0, velocity 0, velocity 1, velocity 2. But we all know that the mass flow rate is equal the area time velocity if you are fixing the mass flow rate coming into the pipe. And if the pipe diameter is also fixed, how come your velocity will increase to be 2 meters per second? In this case, you will get no solution. Or you will get unrealistic solution with crazy numbers, okay? But here, you'll get solution, and you will get the solution within the value of the boundaries, but maybe you got some numerical error, and we will see how to improve that numerical error as we go. But in this case here, you cannot reach 2 meters per second at the exit boundary. So your numerical scheme that's going to keep solving the differential equation or the governing equation will keep rotating about itself and cannot reach that boundary condition, cannot. Okay, it's 2 meters per second, or you will get non-realistic or unrealistic data within that domain, which we know that it doesn't make any sense. So that's how the boundary conditions are very important, because they could lead to no solution or crazy solution because of the bad assumption that you do at the boundary side. So let's get to know different types of boundary conditions. So let's do the types of boundary conditions. there are a few standard cases that we use all the time, or we experience all the time in most of the problem. The first and the most famous one is Dirichlet boundary condition. It's not Dirichlet, it's Dirichlet boundary condition. In Dirichlet boundary condition, you have a fixed value at the boundaries of the body. And I will take one example here. That's one dimension heat conduction problem. Let's assume that you have a solid bar, a cylinder like this. And we are dealing with it like two-dimension problem. So it's going to be like a bar like this. And it's insulated from the top. And since we are dealing one dimension, so we're looking for the flow into one way. That's where Q is coming in or going through. And this is my first boundary. Let's actually have an x-axis here. So x equals 0. This is presenting the left boundary. X equal L, whereas L is the length of that problem domain. So x equal L is presenting the second boundary. So for example, you tell me that, oh, the temperature here is 100 degrees C, and the temperature here is 0 degrees C. And now you are fixing the value at the boundary, and this is what we call it a Dirichlet boundary condition. So you would say that at x equal 0, the temperature at x equal 0 has a value of A, and at x equal L, the temperature at x equal L has a fixed value of B. That's what we call it Dirichlet boundary condition. This is the most famous case we are dealing with. So that's number one. Second type of boundary condition is called Newman boundary conditions. And in this case, I will stick to the same example I have here. So this is your solid bar. This is x-axis. X equals 0 is presenting the left boundary. X equal L is presenting the right boundary. And we are dealing with one dimension problem here. So let's assume that I'm telling you that that bar is really insulated here and insulated here. So now I'm not giving you a fixed value at the boundary, but insulated means what? By the way, insulated, isolated, right? Adiabatic, same word for the same phenomena, different word for the same phenomena, which means that no heat transfer. And in the meantime, it's your maximum temperature. And if you know that if you have a maximum temperature, if you have a function, and this is your max, we know that the slope at that point is horizontal, which means that the slope is equal 0, which means that the derivative of the function has to equal 0 at that point. So when I say that it's insulated, isolated, or adiabatic, it's partial t by partial x, if I'm looking for one dimension, should equal to 0. So under Newman boundary condition, you could say that at x equal 0, partial t by partial x at that value equals 0 is totally equal 0. That's called Newman boundary condition. You are giving me not the value of the function, you are giving me the derivative of the function at that point. And the same apply for the right boundary condition. At x equal L, the derivative of the temperature function at x equal L is also equal 0. And this is what we call a perfectly insulated bar. It's a very common problem in heat transfer. But instead of giving you a fixed value at the boundary, I'm giving you the derivative value at the boundary. That's what we call the Newman boundary condition. The next one which is also very famous. It's just you mix Dirichlet with Newman boundary condition together, and you fix a value at one of the boundaries, and you give me a relation with the derivative on the second end, and that's what we call the mixed boundary condition. So let's write that down. So type 3, or the third type of boundary conditions, mixed boundary conditions. So in this case, you will give me the one dimension example again. This is my x-axis. X equals 0, the left boundary. X equal L. This is a right boundary if the length is L. So what you're going to do, you're going to tell me, okay, at x equals 0, T at x equals 0 has a value of TA, but at x equal L, T partial T by partial x at x equal L is equal 0. It's insulated at one tip, that's why the derivative is 0, and it has a fixed temperature TA at the other side. So this is coming from Dirichlet boundary condition, and this is Newman boundary condition. So you mix both of them, one at each end. We call that mixed boundary condition. The next boundary condition is also famous, but with less cases that we can experience, is Cauchy boundary condition. Cauchy is combining both Dirichlet and Newman, but at the same boundary. Here in the mixed boundary condition, I had separate condition at each side, right? So I have Dirichlet at one end and I have Newman at one end. But in the Cauchy boundary condition, you have both at each end. So if you have a bar and you're solving a one-dimension problem, again, this is the length L, x is equal 0, x is equal L. This is the beginning of my x-axis. So now you will have both Dirichlet and Newman boundary condition at each side, at each end here. So for example, at x equal 0, you will have t at x equals 0 is equal TA, and comma partial t by partial x at x equals 0 has a value of b, which means that this is not perfectly insulated. There is insulation, but there is leak. That's why the derivative is not really 0. Somehow there is leak. But you see that this is Dirichlet. Let me get a different color here. This is Dirichlet. This is Newman. But both are combined at the same side, at the same end, at the same boundary at x equals 0. Maybe you have at the other side at x equal L, I have a different temperature. Let's see TB. And the derivative has a different value. D, or could be 0 if it's actually perfectly insulated. But this is very famous case when the insulation is not really perfect. You got both Dirichlet and Newman boundary condition at each boundary of the body. And I hope you guys can distinguish between this case and this case. The Dirichlet and Newman are separated for each boundary, but here they are mixed at each boundary. That's Cauchy boundary conditions. The last one that we will deal with is actually the Robin's boundary condition. A Robin's boundary condition. Here you notice that I have a mixed conditions at the same boundary. Robin boundary condition comes in that form here. This is a bar L. This is x. X equals 0 is here. X is equal L here. So at x equal 0, you will find that the condition as follow is A plus partial t by partial x is equal 0. You see the combination here, Dirichlet and Newman are separated, but both apply to each boundary. Here, we got a combination of Dirichlet and Newman at each boundary. And maybe if you go at x equal L, you'll find different value b plus partial t by partial x is equal 0. And this is what we call it Robin's. It's again, it's a combination of Dirichlet and Newman. These are the separate one. You combine both of them at separate boundaries. That's mixed. You combine both separately at each boundary. That's Cauchy. If you make a combination of both of them at each boundary, that will be Robin's boundary condition. These are the most famous boundary conditions that we're going to experience all the time when we solve problems. And that's actually all what we need to share into that portion here.